All right, last day, we were looking at using molarity to find volume. Today, we are looking at the final step being finding the concentration. So, we're on page 20. The concentration, when we say concentration, we mean the molarity, which is also known as the molar concentration. And we represent this by putting square brackets. So if you have forgotten this since the mole unit, or if you never learned it in the mole unit, now is the time. If you want to say the molar concentration of, I don't know, NaCl, you will write square brackets, NaCl. And how you're going to find that, that's going to be equal to the moles. What does that line there mean? Divided by liters. So in order to find the molar concentration, you have to take the moles and you have to divide by the liters. Now, if we remember about stoichiometry, when we're doing stoichiometry, what is the first thing we find? What do we find in step 1? Step 1, find moles. Step 2, find moles. Okay, remember, step 1 and step 2 are almost identical. They are almost exactly the same. It's just in step 1, we're finding moles of A. And A is the substance which is the known. And in step 2, we are finding moles of B. B is the unknown. And in step 3 today, so for today, step 3 is take the moles and divide by the liters. So it's going to be the moles of B divided by the liters of B. Divided by. Okay. Oh, he's reaming people out. That's good. I like that. Yeah. Let's get to our classroom. Yes. Okay. All right. So this is the basis of what we call a titration. And so we will be doing a titration lab fairly soon. If not this week or next week, then definitely that last, it actually might be a good thing to do it during that last week of classes, because we're writing our test on the Monday. My marks are due Friday. And so I don't want anything that I really have to mark. Do you know what I mean? Like, so I will just be giving you a completion mark on the titration. I want you to be able to show me your skill as you go through. I want you to just, do the best you can and show me your number at the end, and I'll give you a check mark and a 10 out of 10. Okay?
Are report cards due after?
They're due on the last day of classes.
So I thought it was due after I leave.
Nope.
What?
Yep. Last day for students is the 26th, and then my marks are due the 27th in the morning.
Oh, wow.
So that's just a great turnaround time, right? So I'm like, yeah. Anywho, that's all right. We're going to make it work. Okay. So, needless to say, and I know I'm preaching to the crowd here because you guys were all here for your test. If you think there's any way on earth that you are going to miss that Monday test, you're not. Yeah, basically. Okay. Because I don't have time to mark things after the fact. My marks are due on Friday and I still have to teach all week long, right? Like I got stuff to do. Like I don't have time to be marking your test if you are writing your test on Wednesday or Thursday. I don't have time. Yeah? So don't be away. Don't be late. Just don't. Like, I understand if you have COVID, you're like hacking up a lung, it is what it is. You might not get your report card at the same time as everyone else. I might submit it with like a little comment on it saying this will be updated when so-and-so has written their test, but nobody wants that, right? So just, if you can possibly avoid it, please. Okay? Yeah. Alrighty. So we are starting with usually the volume of solution A. And then we will find, guess what? Moles of A, and then we'll find moles of B. And then we're going to stop because we don't want to find mass, we don't want to find volume, we don't want to find number of particles. We want to do the division. So actually, I should say that this is step 3, right? So step 3, find concentration of B, moles over liters. Let's just jump right into a lovely example. Okay. Where's my mouse? There we go. Okay. So what I might do is I might organize myself by saying I have information about H2SO4. And I am told that I have 15.6 milliliters of H2SO4. I should be converting that to liters. So right now I'm just going to do that 0.0156 liters. So if you would like, you can follow along in the book, or if you want to write it down, there's lots of blank paper at the back of the room. Okay. We also know that it is 0.200 molar, which means we have 0.200 moles per liter. What have I forgotten? Moles of H2SO4. Remember, when we're doing stoichiometry, you always want to have your chemical formula after the moles so you know what you're dealing with. So that's substance number 1. We also have substance number 2, which is our 25 milliliters of NaOH. So we have NaOH. And for that one, we know that we have 25.0 milliliters, which is 0.0250 liters. So who is substance A, who is our known, and who is substance B, our unknown? Well, you look for your question word, and it says calculate concentration of NaOH. So the concentration of NaOH is what we don't know. So that means that NaOH is substance B. That is our unknown. Your known substance is always the one that you are able to find the moles of, and we'll be able to find the moles of that. So H2SO4 is substance A. That is our known. And so let's start. Step 1, find moles of A. I'm not going to do that. We're going to start with 0.156 liters times 0.200 liters, no, moles per liter. That gives us moles of H2SO4. And then we want to find moles of NaOH. So we found moles of A, and now we're finding moles of B. And we need to cancel moles H2SO4. Where do those numbers come from?
Yeah.
Moles of this and moles of that come from our coefficients, okay? So those come from our coefficients, and the coefficient is a 2 for NaOH and a 1 for an H2SO4. And when we are finding molarity, I recommend that you just stop right there, okay? Stop and calculate. So we have 0.156 times 0.2 times 2 is 0.0624 moles NaOH. But we were asked to find the concentration of NaOH. Write this. That's going to be your moles divided by your liters. So that's going to be 0.0624 moles of NaOH per 0.0250 liters. And it's important that when you're doing this question, either you have to be able to see which numbers are related to H2SO4 in your head, or you have to write it down. You see how I've actually color-coded it here. Everything for NaOH is blue. Everything for H2SO4 is red, because you don't want to accidentally use the volume for H2SO4 when you're dealing with the concentration of NaOH, because this needs to be moles of the NaOH. This needs to be liters of the NaOH solution. So take care with that, okay? Don't mess it up. If you want to have like two pens, use one for one and one for the other. All right, so we got 0.0624 divided by 0.025, and we get 2.496. But we have 3 sig figs, so that's going to become 2.50, and our unit is moles per liter. But you could write it as 2.50 molar. Is good? Okay. Let's try another one. And actually, I'll show you this here. You can do this all in one line if you want to. Okay? You know how I did it in 2 lines? I had line number 1 where I found my moles of NaOH, and then I had line number 2 where we found the concentration. We divided moles by the liters. Yes? Did I do my numbers wrong?
In the book it says 0.25.
Oh. Oh.
0.50.
I don't know.
Is this what
It should be 3 sig figs.
But it says 0.
Yeah, let me just 0.01. Okay. 15.6 times 0.2 times 2 divided by 25 equals, yeah, it should be, where did I go wrong? .0156 times 0.2 times 2 equals, oh, there should be 2 zeros in here. 0.00624. There we go. Okay, yeah. Alrighty, but let's wait and see. You can do this all in one line. You can say, I don't know what the concentration of NaOH is. Write this. Write the NaOH in square brackets. Please do this. It's the moles of NaOH over the liters of NaOH. You can do all of that conversion where you have your liters, where you find your moles of H2SO4. You cancel your moles of H2SO4 and you find your moles of NaOH. And instead of stopping and putting equals and finding your moles, you can divide by 0.250 liters just by multiplying by 1 over 0.250 liters.
Oh.
Yes, that is allowed. You can do that. Or you could put all of this over 0.0250 liters, and you could do it like that. I find that's just really awkward and requires a great big huge line, and I don't like doing that. But some people do, and I won't argue with you if you do. Okay? Now, today we're going to talk about titration, because this particular thing is all to do with titration. And titration is a way of finding the concentration of an aqueous substance. To find the concentration of an aqueous substance. And there are a few terms that you are required to know. I'm going to put stars beside them. You need to know them. They will be on your test. Standard solution. The standard has a known concentration. The sample, that is your known volume but unknown concentration. Do you guys remember what a burette is?
Yes.
Those things over in there, those in the corner? See those tall things? You remember those? Those tall things? Those are the burettes. You need to know what a burette is. There is also such a thing as an indicator. An indicator changes color according to the concentration of the acids and bases surrounding it. So for example, phenolphthalein, and that's quite the word, isn't it? I want you to take that in. It's got a PH and then a TH right after it. Phenolphthalein, but you don't pronounce the TH. It's just, or actually you don't pronounce the PH in the middle. It's phenolphthalein. Phenolphthalein. It is pink
Oh, yes.
in acid. No, it is pink in base. Sorry. It's pink in base. And it is colorless in acid.
I don't think we did the lab we did with the, and then someone, a lot of people. was
Yeah.
pink with the phenolphthalein.
That was the phenolphthalein, yes. Okay. So that's an indicator. And what it's going to do is you're going to be reacting, say, an acid with a base, and you'll have an acid in your container. And the phenolphthalein will be in there. If it's an acid, it will be colorless. You're going to start to add base, add base, add base, add base, add base, until the acid is completely neutralized. And then the moment the acid is neutralized and you add more base, now the solution is going to be basic and it will turn pink. Okay? And I'll do a demonstration of this, maybe not today because Fridays are short days, but maybe on Monday. I'll do a quick demo of it and then you'll get a chance to do it yourself very soon. So you need to know indicator. Ooh, you need to know the word titrant. The titrant is the standard. And the standard is the known. So if I were doing this for myself, if I were sitting here, what I would do is I would have my own little piece of paper and I'd be like, oh, standard equals known equals titrant. And then I would be like, okay, I got this other one here. I got my sample, which is my unknown, and it's also called an analyte. Okay, sample, unknown, analyte. Can you guess what word analyte comes from? Analysis. Analyze. Yes? Analyze. Have I done that wrong again? Yes, I've done it wrong. I've spelt it wrong. It is not the analyte, it is the analyte. Analyte. Let's fix it. Yes, because we analyze it. Let's fix it. Analyte. And that's because we analyze it. Does it make sense that the one that is unknown is the one that we analyze? We are analyzing the unknown. So the thing that is getting analyzed is the unknown, and that is our sample. Equivalence point. The equivalence point is the point at which, let's say you had two particles of acid, HX and HX. How many NaOHs would it take to neutralize that? One NaOH would be necessary to neutralize this one, right? No?
How many H's are there?
There's just one H. One H requires one OH. So if I have two HX particles, let's just make it really simple, just two, then it requires two NaOH particles, yes?
Yes.
So my equivalence point is the point where I have added those two NaOHs. I haven't added one, because if I added only one, it wouldn't all be reacted. It would not all be neutralized. If I add 3, more would be neutralized. Or sorry, it would be more than neutralized. So I would have leftover base. Okay, the equivalence point is the point at which substance A and substance B have completely reacted and there is no leftover. Is good? Completely reacted, no leftover. Oh, there's a little bit of margin of error. Yeah, okay. So we do the best we can, but obviously, you know, moles rather than single particles. Yes. And we have to decide when the indicator has changed color, right? How do we know that we've hit the equivalence point? When we've neutralized it all, it's because that's when the indicator changes color. There's another E point, which is the end point. Okay, so we have the end point. That's the point at which the indicator changes color. If you've done a good job of choosing your indicator, it will happen at the same time as the equivalence point. But it is possible to get an indicator that changes pH at like pH 2, in which case it's not going to be very useful for you. Okay? And then we have an outlier, which is a titration value that does not agree with the other trials within 0.2 milliliters. Now, what the heck is that? When you do a titration, you don't just do it one time. You do it once, and you get a value, and you do some calculations. Then you do it twice, and you get a value, and you do some calculations. Then you do it 3 times, and 4 times, and if you don't get good agreement, you do it 5 times. You do it until you get statistically good data, okay? So titrations are always done more than once because, just like you said, there's a margin of error, right? Every time you do it, you're making a judgment call. Is this pink enough, right? Did I spray down the sides of the container so every single drop of the base went down? Or did I forget to do that, right? So every little thing, that's why we do many trials. So here's how it goes. In the flask, what type of flask is that called? You're so close. That is an Erlenmeyer flask. That's a word you need to know. Erlenmeyer flask. And you know what goes in the Erlenmeyer flask? That is your sample. That is your analyte. Analyte. Let's fix that. Analyte. That is your unknown. Okay, so that's what you want to find out. Above that, what's this long tube called? What's that long tube called? Starts with a B. Burette. That is our burette. Okay, and the burette contains the standard solution. That is what we call our titrant or our known. We call it the titrant because we titrate with it. So what do we put in here? In our Erlenmeyer flask goes number 1, our sample, and number 2, our indicator. In our burette goes the standard solution. And then we drip, 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 drip until we see a color change. You guys don't seem at all interested in chemistry. I wonder why they take the course. I don't know. Are you guys at all interested in chemistry? Yeah? You don't seem like it. Like, it seems like you're like, I don't know. Am I that boring? I mean, I know it's not interesting to necessarily sit here and just listen to me talk, but first you hear it, then you see it, then you do it, then you have many ways of accessing the knowledge. If you don't hear it, then you don't have that way of accessing the knowledge. If you don't read it, you don't have that way of accessing the knowledge. If you don't do it, you don't have that way of accessing the knowledge. I want you to have all the ways in your brain. I want you to have 5 different sets of neurons with this knowledge in it so that you don't forget it. Okay, so drip, 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 drip. See the color change? Ooh, la, it's done. Okay. And then we do our stoichiometric calculations. We are going to repeat this process. At least 3 volumes are within 0.2 milliliters of each other. You need to know that number. Okay, if you have something that is not within that limit, like let's say one of our volumes was 10.00 and we had 10.02 and then we had 10.07 and we had 10.01. Which of those 3 data would we use? Which of those 4?
10.0, 10.01.
These 3 are within 0.2 of each other. The 10.7 is out of bounds. Now, when you do your titration, you might not have time to do 4, 5, 6 things. We sometimes fudge a little bit because it's your first time through and you don't always get data that good. And we're like, close enough, right? But we're going to give you some data here that actually gives you good data. If you have this 10.7, that 10.7 is the outlier, and you will not use it in your average.
So the point is, the point 2 is intense, right?
Yes. Oh, within 0.2. Oh gosh, I'm so sorry. Let's make that better. Yeah, those would be really good data. 10.20, 10.10, 10.70, and 10.00. So these would be good. This would be our outlier. Thank you for catching that. Yeah, no, it should be, yeah. And it's really hard to get within 0.02 of each other. We would not want to be having to be to that standard. So our average volume then, do you guys know how to take an average? Add it together and divide them. So we're going to take 10.2 plus 10.1 plus 10.0 milliliters divided by 3, which gives us 10.10 milliliters. And that is the number we would use in our calculation. Okay? So here's a picture of what's happening. We have 10 milliliters of HCl. Here it is. We put it into our pipette and the pipetter. Okay, we have a pipette. Have we used a pipette yet? Have we? Okay. I feel like maybe we have. Yeah. So there's our pipette, and we use a pipetter. Do you guys remember we roll it up? No? Okay, maybe we'll try that today if we have time. Okay, so we take our 10 mils and we transfer it into the Erlenmeyer flask. This right here, 10 milliliters. We do not know the concentration of the HCl. Then in here we have our NaOH, and we put it into our burette. So in here is the NaOH, and we measure our initial volume. Do you guys remember doing that? You measure your initial volume? Yeah. And it is 3.11 milliliters. Remember, burettes read which way, up or down? Durette's read down. Good. All right. And then we add a few drops of the phenolphthalein indicator. So down in here now we have 10 mils of HCl and we have phenolphthalein. Why is it writing so funny? That's weird. Oh well. Then we turn this little doodad here, the little nozzle. That's called the stopcock. I'm really sorry, that's just its name. Nothing I can do about it. That's what it's called. We can call it the valve if you prefer. Yes? Well, why do you think a cock is called a cock? It's called a cock because it lets out liquid. That's where it came from. It's true. It's true. And I'm sorry, that is what it's called. You can call it the valve if you prefer. If you're like, I do not want to call it a stopcock, that's fine. But that's what it's called. All right. Oh, you don't want to take chemistry 11 enriched? Because we have to talk about orbital penetration. And I'm like, I don't want to talk about that. But that's what they call it. And all it is that the electrons get closer to the nucleus. But that's what they call it. I'm like, oh my God. Okay, anyway. So we start dripping in our NaOH. Drip in the NaOH. And you'll see right now that this is colorless. And it remains colorless until all of a sudden it turns pink. When it turns pink, we have reached the end point What is the end point?
Yeah, it's one. When the thing like changes color.
That's when it changes color, okay? That's when the indicator changes color. And if you're like, what is that triangle doing there? What does delta mean?
Changes.
Change. So that's changes. So when the indicator changes color. So we have reached the end point, which means we have also reached the equivalence point. No. Okay. And we spend actually a lot of time in grade 12 looking at that, where we're like, which indicator should you choose? This one will change color halfway to the equivalence point. That will be useless to you, yes? And you'll learn how to predict which ones will change at the correct pH. Yeah, okay? For grade 11, you can just assume that your teacher has done a good job of choosing the correct indicator, so the end point will occur at the same volume as the equivalence point, okay? So we've reached the end point, which means if we chose the right indicator, we've reached the equivalence point. Please tell your partner what the word equivalence point means to you in this moment. It might not mean a lot, but describe it to your partner. What is equivalence point? Okay, it is when A and B have reacted completely. there's no leftover of either reactant. So all the acid is gone, all the base is gone. All you have is the salt and water. Okay? If you continued to add base, you would then have a basic solution. Okay, so let's go back up here and take a look at our data, because what we had is we had HCl, which is our unknown, which is substance B. What would we call the HCl? The HCl would be the... What are some other words for the unknown in a titration? Analyte. And you can remember that because it also starts inappropriately, just because we're doing that today. Sorry. But you won't forget now, will you? Anywho, so this is our unknown. This is substance B. It is also known as the sample. Okay? So that is our substance B, is the HCl. NaOH, which we've got in red over here, we have an initial volume. We drip, 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 drip. And then we measure our final volume. We've got a final volume. So we have 15.82 milliliters. And our initial volume was 3.11 milliliters. What was the volume of NaOH used? How would we calculate that? That would be VF minus VI. I probably have the calculation down at the bottom. Shall we see? No, I don't. Oh, yes, I do. There it is. Our volume of our NaOH is equal to VF minus VI. We've got 15.82 minus 3.11 milliliters, and we get 12.71 milliliters. And somewhere on the bottle of NaOH, it will give you the concentration. Okay, somebody has measured the concentration of that substance really well, and they're letting you know that it is 0.9973 molar. Okay? And you should be able to write a reaction for that. It's really, really straightforward. And I think probably on the next page, oh, there we go. Look, after all of that, we've organized our data into our unknown and our known. Okay? What's another word for the unknown? That is our analyte. It is also known as the sample. Nope. Did I write that somewhere? Hang on, let's see. Nope, analyte is the sample. The standard is the known. Okay, so our unknown is the analyte, that's our sample. The known is known as the standard and also as the titrant. 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 And then at this point, this just becomes stoichiometry, which I hope is becoming more easy for you. You're going to say, okay, I'm going to take these two guys here and I'm going to find my moles of NaOH. So I'm taking my liters of NaOH and my molarity of my NaOH, I'm going to find my moles of NaOH. That's moles of A. And then we're going to find moles of B. And then we're going to find the concentration of HCl by taking the moles and dividing by the liters. So what that looks like then is 12.71 milliliters, that's 0.01271 liters, times, don't forget when you have molarity, you have to write moles of NaOH. We want to cancel moles of NaOH and find moles of HCl. Where do we find these number ones? Where did those come from? How do I know that there's 1 mole of HCl for 1 mole of NaOH? Those are from the coefficients. And the balanced reaction is just up here. So you can see there's a 1 there and a 1 there. So step 1, find the moles of NaOH, you're known. Step 2, find the moles of HCl, you're unknown. Now we want to find concentration of HCl. Write this. Square brackets around, HCl equals, and then you put your moles and you divide by your liters. Moles divided by liters. You cannot find molarity by converting it. You cannot take moles and convert them into molarity. Like there's no way where you can go, okay, I'm going to take moles and I'm going to multiply by a conversion factor and end up with moles per liter. I don't want to cancel moles. I want it to stay there. The only thing I could do is I could put a 1 on the top and I could put liters on the bottom if I wanted to, and then I'm not converting, then I'm just dividing. Okay, you could, like I just said, divide by putting that as your last step and just having a 1 on the top. This is not a conversion. This is a division. So we got some exercises here for you to practice on. I just want you to take a quick look on, what page is it on? There is one question back here, question number 5, where you have some more actually realistic data, where you have trial 1, trial 2, trial 3. Look for an outlier. All right, so you guys for homework are going to be completing the questions for 7.1D. Okay, that is pages 23 to 25. Okay? Yep, only for single replacement.
The states is only for single replacement?
Yep.
Oh.
You could use it for the states for single replacement. If you're doing states for single replacement, you could also use it for the states as for the salt in a neutralization if you wanted to, but that's only enriched.
Oh.
Yeah, it's not necessary.
And then, but the solid is
Only double replacement. Yeah.
And for the enriched,
Yeah.
I don't know the organic things, but I know like the alkaline.
That's okay. So I can give you the formula of the acid and you can do the other one yourself. Okay? Yeah.
Should I write it like in a corner somewhere?
We can put you in the back room if we want to, if you'd like. It's nice and quiet. Yeah, yeah. Yeah. I'll be with you in just a sec, Sabina. I've got to get a test set up here. Hi.
Do you have final test for this course?
We have our stoichiometry test, which is basically like a final because it includes moles and formulas and reactions and everything.
And the work is like the previous.
No,
Oh,
uh-uh. Just double. And in fact, you don't, well, yeah, yeah, yeah.
They just need to you stare at something for a long time.